Hello and welcome to the iRevise Supplementary Series for A-Level Physics. This video is a bit of a continuation of the astrophysics. It's a bit of a hodgepodge. I want to talk about gravitational fields, orbits, Kepler's laws. This is a little bit more detail than what you see in the Leaving Certificate, the Irish curriculum. So they do circular orbits and they do these sorts of calculations. I don't know if explicitly if they talk about Kepler's laws. I don't know explicitly how much they get into gravitational fields. So I know, for example, some exam boards, WJEC, they really get into the idea of dark energy and orbits of galaxies and some things which are a little bit beyond the Leaving Certificate scope. I'll do some questions on escape velocity. There are a few exam boards that do projectile motion, AQA for example, so we might do a couple questions there. We will skip past parts of questions which deal with the universal law of gravitation or Coulomb's law, anything with circular motion, calculating periods and orbits and stuff, unless it's a little bit more intricate, maybe a little more interesting, and questions which can help drive some important points home. Okay, we'll also take a look at electric and gravitational potential. Now, I know that a lot of curricula will take a look at electric potential, potential difference, and just talk about that as the voltage and do it in terms of the circuits. Some courses, like WJEC, for example, they do a real strong, their unit is electric and gravitational fields and potential together. I know Cambridge Pre-U and some other exam boards look a little bit more at gravitational potential, and so that's the bulk of what I want to do in this video, linking all of these calculations I was just talking about to gravitational potential. We'll look at equipotential lines, and we'll just try to supplement whatever is not in the Leaving Certificate. This video is part 1 of 2. Okay, let's get on with things. Here we have an Edexcel Paper 2 Advanced Physics 2 version, and that's from 2018. In 2015, the Messenger spacecraft crashed on the surface of Mercury after 4 years orbiting. The orbit was highly elliptical, varying between 200 kilometers and 15,000. The Messenger completed one full orbit every 12 hours. Okay, it's been suggested the same orbital period of about 12 hours could have been achieved if it was a circular orbit. Determine whether this suggestion is correct. This is like a Kepler's law situation here, isn't it? If we wanted to, we could put in a radius here, we can plug it all in and see if we can get that period. That's one thing we could do. Okay, I think you might also see, if I take the universal law of gravitation and set it equal to the centripetal force, I think you'll see where this equation comes from. These masses are going to cancel out. I'm going to lose an r here. Okay, now we also know that v squared is going to be this circumference divided by the period. Okay, and let's plug that in. What are we going to end up with? We're going to have gm over r is equal to 4 pi squared r squared over t squared, and I think you can see that rearrangement coming back out to there. So I'm going to tell you, if you are studying Kepler's laws in your curriculum, maybe you can just jump to this, okay? And I have a nice way of remembering this. Yeah, you know it's t squared equals 4 pi squared, and remember the r cubed, it's just 1 above the pi squared, and it's over gm. I think it's a nice equation to remember, and it'll save you all of that work unless they want you to actually show that. Okay, so we can plug all of our values in there, but we need to think about something here. This radius cubed, what is this radius that we need to put in exactly? Okay, because what we need is from the center, this orbit, yeah, but then we've also got the radius of the planet to consider as well. That needs to be included because it's acting on the center of the planet. So those need to be added together. All right, so I get 1.012 times 10 to the 7. All right, so I get 43,115 seconds, and if you divide by 3,600, that should give you 11.97 hours. So I would say we've done it. We've done the calculation. We can say, hey, yeah, that's correct. It's close to 12. The elliptical orbit has advantages over the circular orbit. Explain one advantage. Well, you can be really close for zoomed in shots. You can also kind of back away and get the whole planet in the picture if you like. I'd say something like that. Let's go take a look at the marks. Okay, so here's our calculation. Yeah, we did this. We got it to work. Here's an example of how it might work. That's what we did. Other ways you could have done this. You could have figured out the force separately and then done some equating. You could have figured out angular velocity if you wanted, but I think this is fine. Comparative statement consistent with your values. So you can't just do the calculation. You do need to say, hey, therefore, yeah, they were right. It's close to 12 hours. Okay. Some advantages: maximum of 2. They'll allow you to say, so it allows the satellite to get much closer to the surface, so more details. That's kind of what I said. I had also said satellite varies distance from the surface, so you can take wide angle and close-up pictures. So I don't know if they're allowing you to mix and match those. I think it's because they had explained one advantage. I guess the advantage is either more detailed photographs or different range, like close-up and wide angle. Those are two different things. You need to talk about how you can get to do that. That's because here you can get closer to the surface for the detail, and here it's variable, so you can get different wide angle or close-up shots. Okay, and then one which I didn't really think about, but maybe some of you did. It allows the satellite to spend further time in space because otherwise prolonged heat from the planet. Okay, and so that's interesting. Okay, and the last part: calculate the velocity an object would have reached from the surface of Mercury if it was released from Messenger's maximum orbital height. Assume the object has been released from rest and that Mercury has no atmosphere. Okay, so we draw ourselves a little diagram. We're up here. Yeah, this is going to be, is this the initial radius? No, the initial radius is going to have to include the radius of the planet as well, okay, of Mercury. And so this will be your final radius because that's what's left over. This is the initial distance, this whole thing. So we're going to have to add the radius of the planet we were given, and we're going to have to add the 15,000 meters to that, okay? Well, the 15,000 kilometers. That's going to give us 1.743 times 10 to the 7. Set this up. The energy before equals energy after, that kind of initial, final, whatever you want to say. So we're going to have a half mv squared. Now, we know the equation for potential. We're not going to just plug FMGH because you know the gravitational field strength is inversely proportional to the distance. So we don't want to do that, but we are going to put in our potential. Now, I'm going to write in GMM over R because let's just remember that gravitational potential is GM over R. Okay? Now, what's potential mean? It's the energy per unit mass. So if I've got energy per unit mass times the mass, I'm actually got energy then, don't I? Okay? This is no longer, I'll do it on both sides, okay? And what we're saying is mass times this change in gravitational potential, that's going to be the change in energy. That's going to be the work. That's how that works, all right? So that's why I've got this M here. I'm going to do 1 here over R. Now, the M's can cancel out. We can drop them. We need to identify which radius is going where, okay? I've actually, on the left side of the equation here, I've got the final velocity, don't I? Because this thing's falling. We want to know the velocity when it reaches the surface. So this is the final here, and this will be initial here. I have them switch sides. What we can do is we can say v squared is equal to, we can do 2 GM. And what we'll have is a difference of inverse radii here. So this thing on the right side has not changed. It's not moving. It's not gone anywhere. So I'm going to put the initial here. And this one, which was the final 1 over, it's going to move over and be positive. So it's going to go first. Now this should make sense. This should work out because we're going to have the reciprocal of a smaller number, which means this will be larger. And we'll be doing the reciprocal of a larger number. That'll be smaller. And so this will end up being positive. And you need it to be positive in order to get a square root for your velocity. Plug in your mass of the planet Mercury. And when you plug everything all in, you get 3,900 and let's say 48 meters per second. Yep, that's what we got. That's good. Okay, so there's some calculation information there on the right if you like. Use of the gravitational potential, multiplying it by the M to get your... They say EP, but that's gravitational potential energy, right? Okay, so you get a mark for doing that. So let's see. I've erased it now. I've erased it because I ran out of room. Hopefully you would keep that there. I'm illustrating what to do in an exam. I'm erasing stuff. Hopefully you wouldn't. You need to include that, okay? Or maybe when you set up your equation and you cross out the m's, you can say, hey, this is because we need to make it energy. You know, just make a note of what you're doing. Subtraction of potential. So you could subtract the potentials first and then figure out the change in energy and then change the and then equate the change in energy to the half mv squared. You could do that if you like. That's fine. You calculate it how you like, and hopefully you get it. This is a paper 4 from the Cambridge Board 2016. They're going to give us the 2 radii, and they want us to determine the ratio for the velocities and the periods. Well, we've got this expression here already now, don't we, right? So, square root of gm over Ra divided by the gm over Rb. We'll do some canceling, and you'll see that we get the square root of Rb over Ra. Now, really, the shortcut should be this. The shortcut should be, hey, I know that radius and velocity are inversely proportional. So, and there's a square root there. And so the b is going to be on top. It's going to be root Rb over Ra. That should be fairly straightforward and maybe very quick for you to come up with. Right, and that gives us a ratio value of 13. And look, we could try to plug this all into the thing up above, but I think if you recall correctly from your Kepler's law, I think we already know how we can sort this out. So the ratio here, I'm going to say that our ratio of TA over TB, okay, since we were given the radius, all right, we are going to see here, it is going to be the square root of Ra cubed over Rb cubed. And all these other things are going to cancel out. That's what I'm predicting we should have.
You're amazing. You figured this all out already.
Now, we've just calculated this ratio here, so that's fine. We know that the orbital velocity is going to be the circumference divided by the time. Okay, so if we were to rearrange, we know that time is going to be 2 pi r over v. The 2 pi's are going to cancel out. What we'll get for our ratio here is we're going, again, you can see it's proportional to r, inversely proportional to v. So that'll be Ra over Va over Rb over Vb. And again, we'll rearrange. We'll have Vb over Va times Ra over Rb. Right, now we know the value for VA over VB is 13, but we also know that the value for VA over VB is, you'll note here, it's the root of RB over RA. If I wanted to, yeah, we could say that this VB over VA is the root of RA over RB times RA over RB. Now hold on a minute. Doesn't that actually give us RA over RB? What is this now? That's to the power of 1.5. That's to the power of 3/2. To the power of 3/2 is the same thing as saying root of RA cubed over RB cubed. In other words, the quicker way to have solved this might have been to use Kepler's law.
You got a gift, my friend.
Now, is that not the same thing that we have now? Yes, it is.
You're very perceptive.
So what we can do is we can take our value here, which was 13. Well, we're going to have 1 over 13, and we're going to cube it, because this was the root of RB over RA, and now what we're going to have is, it's like saying the root of RA over RB all cubed. It's 1 over 13 cubed. And that gives you 4.54 times 10 to the negative 4. That's a quicker way than you plugging in these numbers a second time and sorting it all out. Look at how that helps out for you. Know your exponents. You can go through things a lot quicker. Going to the mark scheme here, we calculated the ratio to be 13, and therefore we saw that if you multiply, you can either use Kepler's law or you can use the other method too. Either way is fine.
Kudos, Elaine, on a job done.
All right, I've got paper 4 from the Cambridge Exam Board 2017. Define gravitational potential at a point. Well, gravitational potential is the potential energy per unit mass. So I would imagine we're going to be saying it's the work done or the energy needed per unit mass to do something. Well, what is it? What is that something? Usually, traditionally, it's the work done in moving an object from infinitely far away to a certain location, a certain distance from another point. So something to that effect. Moving on, we've got a rocket here. There's a point A and there's a point B. This is the path of the rocket. You can see the different radii and distances labeled there. Right, so point A is a distance r, point B is a distance 4r. Show the difference in gravitational potential between points A and B. Okay, so I've written my expression here. I'm going final minus initial. Okay, so I've got R2, and then on here subtract negative GM over R1. What's going on in this case? R1, is it going to be R? No, we need to take into account the radius of the planet as well. So that's going to be 2R. Okay, that means we're going to be 5R away finally. Now, what we'll need to do is we'll get ourselves a common factor of 10R. That means we're going to have 2GM minus, negative 2, this is a negative here, and this is the plus. This is a plus, this is a minus of negative 2GM plus 5GM. And so this is where we get 3GM over 10R, like they've asked us to show. It's 1 mark, so I don't know how much you need to show, but it really shouldn't be much more difficult than something like that, okay? Plugging in these radii values. Okay. On to part 2, which I've sort of started here already. They're talking about, they give you the mass of the rocket, and they're talking about the change in energy. So I'm going to put a mass times that change in potential. I'm going to put a mass times this 3GM. They told us to use the expression from above, so the 3GM over R times little m. And if you plug everything in, you should be able to rearrange for R. I've taken this difference here, and I put it down there underneath, okay? Now, what we might notice right away here is, well, wait a minute, 0.88 minus 1.7 is a negative value. So why don't I have a negative here? What's going on? I've dropped really what I've done, because this is final energy minus initial energy. What we should really be looking at is, we know that the loss of kinetic energy is equal to the gain in potential energy, isn't it? Okay, and so what we're saying is the change in kinetic energy is equal to the change in gravitational potential energy. But you might be saying to yourself, well, wait a minute. If it's a loss in kinetic energy, it's actually a negative. So what you'll need to do is you'll need to put a negative out in front, is technically what we've done. If you have a negative loss, which is a implicitly negative value, we'll make it positive. You can't have a negative value. You can't have negative 3 equaling 3. Okay? You can't have negative equaling positive, and so we put a negative out in front there. Okay, that's what's going on. That's why I've got that as a positive number. All right? But this whole thing is equal to R, isn't it? And I get 6.88 times 10 to the 6 meters. Now, that what we've calculated is R, isn't it? That's what this is here. But they want to know the difference from A to B, don't they? And it's from the surface to B is 4R, from the surface to A is R. So I'm guessing it's 3R, okay? Because they want to actually determine the distance from A to B. So this is R, so we'll have to do 3R. And so that's 2.1 times 10 to the 7 meters. All right, let's take a look at the answers. Right, okay, so work done per unit mass in bringing a small test mass from infinity to a certain point. That's our definition. This seems to be universal across exam boards. Okay, we've showed very simply how we got that. That's fine. The change in PE, you could have done that separately. I did it all at once. We got that as a radiance, and then you need to triple it in order to get that distance. Well done. Okay, this is a Cambridge Pre-U paper, paper 3 from 2013. So a rocket launches a satellite. State the relationship for the gravitational potential energy E of the satellite in terms of the relevant quantities given in the figure, so in terms of the speed and the mass and all that stuff. Well, look, gravitational potential energy is going to be mass times the potential. We know that's G, big M, little m, over R. It'll be negative, and but that's actually our that's a little r, isn't it? That's our radius to the center of the Earth, and so that combined is going to be r plus h. That'll be our answer there. What is meant by the term gravitational potential energy? Remember that the potential was the GPE per unit mass. This is just GPE. So we could say, hey, look, it's the energy required to move an object from an infinite distance up to a certain distance from that larger mass. Something along those lines, I would imagine. Why don't we have a quick look? Yeah, so that's our formula that we had. I had the negative in there, yeah. The amount of work done on a mass, or energy needed, to move an object from infinity to a point where the satellite is, or from infinity to a specific point. That's the definition that we've seen repeated over and over, isn't it? Okay, in part 3, use this information below to determine the height of the satellite above the Earth's surface. Now, I might be tempted to do it this way, but if you just take a real close look at what's going on in this question. This is a part 3. Here we've done a part I, so we're going to use that equation maybe, and then they're telling us what's going on with this. Yeah, the amount of work done. Yeah, we've just said here, what's the definition? It's the work done. It's the energy needed to do. It's the work done. Okay, so yeah, work is change in energy. We also know that the total energy here is going to be the kinetic energy plus the gravitational potential energy. And since we've got that expression there for gravitational potential energy, if that's already there, and it has the H that we need, and then we take a look at, they give us the total energy as well, don't they? So maybe we want to just take, hey, 4.5 times 10 to the power of 9 equals, and we'll use the half mv squared for the kinetic energy, and we'll just get that term there. Maybe that's what we do. Okay? So if we take 7.7 times 10 to the 3 squared, half of that times 152, you'll get an interesting result. You actually get 4.5, get this, times 10 to the power of 9. So that's interesting. We bring that to the opposite side, and now we've got negative 9, and we've doubled that energy, haven't we? Just funny it works out that way. Anyway, so this is what we'll have when we rearrange. We substitute everything in. Notice these negatives will cancel out, so that's convenient. That's good. We need a way to get rid of that negative. We had negative total energy. And when we plug this all in, 3.76 times 10 to the power of 5 meters. So, what's 376 kilometers, yeah? Right, and that's the answer for the calculation. And so they've done it that way as well. They've done the energy, and they subtracted it. And why would we do this way rather than this way? Well, you'd have a lot more rearranging to do and whatnot. And the fact that they've actually given us this energy right here, well, the total energy anyways, they give us the total energy, and you can very easily calculate the kinetic energy, kind of makes it a lot simpler. So you could definitely do it this way if you like. It will work out, but it's just a little more work for you. Okay, and I've got a paper 3 from 2011. This is the pre-U syllabus. Okay, now the gravitational potential energy of the moon. Remember, gravitational potential energy will not be mgh. Okay, the gravitational potential is gm over r. If you want to find out what the potential energy is, the gravitational potential energy, it's mass times that change in the potential. It's just like if you want to find how much energy a charged particle has, it's the charge times its electric potential, okay? It's the mass times its gravitational potential. That's what's going on here. And so what you end up getting is your gravitational potential energy, depending on whatever notation you use, you're going to get mass times that potential. You're going to get gm little m over r. So you plug it all in, you get 7.63 times 10 to the 28. And of course it needs to be negative because it is in a potential well. That's why the moon is in orbit. Going to plug in these answers from up above down here. Give that the total energy of the moon is constant during one orbit. We should be able to complete the table. Right, okay. So we add these two values together. We get negative 3.79. You'll get negative 3.79. Negative 3.79, okay. Negative 3.79 minus negative 8.24, and I get here 4.45. Does it make sense that when we've got the lowest amount of potential energy, we've got the highest kinetic energy? That's closest to the Earth, and so the orbit, its speed is the fastest. Okay, we can imagine this to go lower. We can imagine this to go, I'm going to say lower, but what I mean is less negative. It's going to go closer to zero by lower. So how are we going to calculate that? Well, we could say, hey, I know that the energy is equal to gmm over r. If I bring this up to be ER as in energy times radius, and everything else is constant, that means I can say E1R1 equals E2R2. And if I want to find out what that second energy is here, E2, yeah, that's going to be E1, which is this initial energy, this initial gravitational potential energy, and it's going to be a ratio of R1 over R2.
Check out the big brain on Brad.
So we could do it like this, nice and simply, and you can see that this ratio is less than 1, and we will get a lower energy like we had wanted, like we had predicted. And I get negative 7.19. Probably round that actually to negative 7.2. And it's the same thing we did before, and I get here a 3.14. Let's see how we've done so far. Yeah, so that was the energy. That's what we had calculated there. We had placed that number down here. We had also taken our kinetic energy and put it here, so that's good. And I imagine they give you errors carried forward. It doesn't say on this mark scheme. And then, so 1 mark for saying you've added these. These need to be the same, so B, that's your second mark. C, you calculate this. I think we've done a nice, clever little ratio, and there's just some simple subtraction with some negatives to get these answers, and I think we've got them all. Okay, this is from the 2017 Edexcel Paper 1, Advanced Physics 1. I've got a projectile motion question here. There's the range. There's the height they start from. A shot is thrown from H above the ground with an initial velocity. The time it takes for the shot to reach the ground is here. There's the angle. Show that the vertical component of the initial velocity is about 8.6. Yes, so very simply, this will be the sine component because it's opposite that. So our vertical component is going to be V sine theta. And that gets you 8.55 meters per second. Of course, it should be lower than the 14.2. I hope that's good for you. Calculate the height above the ground from which the shot was thrown. Oh, what's this h going to be then? Okay, well, we should have a simple kinematic equation, shouldn't we? Okay, if you plug this all in, I get negative, it's about a negative 2.3 meters. Now, you might be saying, well, why is that negative? What's going on here? Okay, and the reason it's negative is because we started up here. That's technically the level, and we've fallen down 2.3 meters. So that's why it's negative, but that's the height difference, 2.3 meters. Okay, and calculate the horizontal distance r for this throw. Well, we know that the horizontal velocity is going to be 14.2 cos 37, and at that horizontal distance is just going to be the horizontal component times the time. So the time is 1.98, and that's your range. And it looks like this is, of course, 22.5 meters. This is, of course, assuming no air resistance or friction. Right, so for the first bit, for the vertical component, yeah, we got that use of V cos theta. Oh, where the theta is the angle between V and the vertical. Okay, we should, I always tell my students, always relative to the horizontal, especially for projectiles and stuff, so that you can get into the use of the convention that you want the sine component. But I suppose if you were solving for that angle there, it would be the cos component. That's fine. everything's looking good here. We got that. We started 2.3 above ground because our final answer, we landed 2.3 meters below where we were launched from. Now look at this. Pay very close attention here. If show that value used was h.2. Okay, and then moving on, we got the component times the time, and there we go. Straightforward stuff. All right, moving along on the same paper, we've got this question here about motors and power. I'm going to skip past this rotational axle stuff. I'm going to skip past this torque and that sort of thing. I want to look at this question here about the equipotential lines. In the diagram on the electric field lines here, to the diagram, yeah, add directions of the field lines. Okay, so we can do that. We know that these arrows are going to be going out from the positive, in towards the negative. And I'm going to draw my arrows. Yeah, maybe I draw them here. You're going to see why, because in a minute we're going to want to draw the lines of equipotential, and I don't want these arrows to be in the way. Now, lines of equipotential. Well, if these are two same charges, just opposite, I think we can see the symmetry, and I would draw a dotted equipotential line across. And the point halfway between should be where the force is the weakest, okay? Because it's equidistant between the 2 points, okay? Make sure it's horizontal. Mine seems to be off a little bit, but don't go any more exaggerated than that. We should draw some other equipotential lines, and this is where we might get into some problems because I don't want to get in the way of my arrows here, okay? But if you were to draw a certain distance from your charge, lines which were perpendicular to those field lines, a bit sloppy there, but then you can kind of see, and I would do something similar here. I would say anything perpendicular okay, and you can kind of say that those are my equipotential lines. Now the arrows aren't in the way. Let's see what they say. Right, so we've got arrow away from charge or towards the charge. I don't know how many arrows they actually wanted. They wanted directions of the field lines, so yeah, I've done it everywhere. Show at least and here's the thing, show at least 3 equipotential lines perpendicular to field lines is what we've done, okay? And as you can see in the lovely diagram that they've provided, okay, it's symmetrical, not only about the horizontal axis, but this vertical axis as well, okay? And none of these equipotential lines are crossing or touching. None of the field lines cross or touch, so none of the equipotentials should be because they're perpendicular to that, okay? Now, I don't know, you could get into if you wanted to further out, you could say, hey, this is perpendicular and this is perpendicular. You could get some kind of weird shaped, but I'd keep it simple by going kind of close into the charge, and then you've got that, okay? So that's what we've done, 3 easy marks. Okay, and I've got a Cambridge Pre-U here, paper 2 from 2017. Define gravitational field strength. It is the force per unit mass. Okay, you know that the units are Newton per kilogram, so force per unit mass. Write that out. Let's see here. This is a region near space. Draw 5 solid lines with arrows to represent the gravitational field strength in this region. Okay, now be careful how you draw these. If you're going to draw, grab yourself a ruler and space them out evenly. Okay, draw them vertically. I'm on a tablet. I know you can do better than me. Okay, and then it says draw a dashed line that joins points of equal gravitational potential, so an equipotential line. And that's what a contour line on a map is, okay? Think of your geography class. Those are all the similar elevations, and therefore those are equipotential lines. That's what a contour line on a map is. Okay, calculate the gravitational potential difference between P and the surface of the Earth. Okay, so P is okay. Right, so gravitational potential is G big M little m. Oh, that's the energy. It's big G M over R.
Not a great plan.
Wow. They didn't give us the mass. I don't think they're going this advanced. I think they're going to tell us that the gravitational potential is simply G delta H. The change in potential is G times the delta H. So 9.81 times this 15.5 gives you 152 joules per kilogram. An object at rest P is dropped, and it falls freely until it hits the Earth. Calculate the maximum possible speed. We know that the potential times the mass is equal to the energy. That's going to be equal to the kinetic energy, and the m's are going to cancel, and V is just basically 2 times this potential square rooted. We had said in a previous question that it was gm over r. That's what the potential is, gm over r. So 2 times 152 square rooted. So that's 17.4 meters per second, let's say, and yeah, that's what we get. And yeah, I'm surprised they didn't go with the potential, but I suppose if you plugged in the mass of the Earth, it really wouldn't matter, and so we got that right. Let's go back up. Yes, force per unit mass. Okay. Notice in this exam board they didn't say draw the equation and then explain what the variables are. I think you need the actual definition. Okay. 5 vertical lines equally spaced by I, because the field strength is uniform, and you want the arrowheads going down, yeah, obviously, and then 1 dashed horizontal line anywhere. It doesn't matter for your equipotential. This is a pre-U paper 3 from 2011. Define electric field strength. It's the force per unit charge. Okay. Just kind of similar to this previous question, except with electric fields, right? So a charge is moved through potential difference. State the expression for the work done. The work done for moving the charge through the potential. That's what that is. That's the work done. That's the energy. This is your definition of your electron volt, isn't it? Okay. Show the uniform electric field in the electric field strength is equal to the potential gradient. The work done to move this charge in an electric field, we're going to move it a certain distance, and we're going to have to exert a certain force. Force through a distance, force times distance. Okay, we'll ignore the cos theta. We'll pretend that the theta is 0. Now, what is that force? That force is, if you remember what electric field strength is, just from up above here in part I, we'd said it's the force per unit charge. So force per unit charge, that means the force is the electric field strength times the charge. Now, I like to tell my students about EQ. I call this the electric weight. Okay? Let me write it the other way, actually. QE. Just like we have a gravitational weight, a force of gravity is mass times gravitational field strength, and the weight, that's a special term we've given to the force of gravity acting on an object. Where it's
more correctly, it's the force that an object experiences in our gravitational field here on Earth. Now, an object can have an electric weight, it can have an electric force, and that will be determined by its charge times the electric field strength. So I very much like this idea of this electric weight going through a distance. Just like when you move a book, we saw it in the last question, when you move something up on that hill,
and it was just as simple as MGH, when you want to change the gravitational potential energy, yeah, you're taking the weight and you're multiplying it by the distance you move it, and that's the force through that distance. It's a vertical distance, but there you go. Now with charges, doesn't matter what direction it is, but we have an electric weight, and that's the force, and it's going through a distance, so it's QEX. QEX is equal to QV. And we can see here that it doesn't matter what the charge is, just like it doesn't matter what the mass is when we talk about potential energy and transferring it to kinetic energy. The mass is irrelevant, isn't it? And it's the same type thing here. And so what are we going to see? The uniform electric field, the field strength, what do we get here? The field strength is equal to the potential gradient. And here you get your V over X, your potential gradient.
Okay, and I've got an AQA paper 2 here from 2017. State what is represented by gravitational field lines. Well, with any field line, what we're doing is we're representing the strength of that field. Okay, so I would just say, the closer the lines, the stronger the field, something like that. Tricky for 1 mark. We'll see what they say. Figure 6 shows a gravitational field of a small horizontal region over the surface of the Earth. Suggests why the field lines converge over a small area at K. Well, it must be a stronger field there at that point. Maybe that's a dent in the ground. Maybe it's something a little bit below sea level. And so if you're further down towards the center of the Earth, you'll have a stronger gravitational field. That would be my guess.
A ball traveling at constant speed passes position J and moves towards position K. Explain any change in speed of the ball as it approaches. Well, it doesn't say which direction, but I imagine if it's going from J to K, it's going horizontal. It says friction is negligible. So it would be falling towards the Earth as it moved to the right, but it would start falling faster as it approached K, I would guess. How are we doing on the mark scheme so far here? Gravitational field lines show the direction of the force on a mass. Wow, lots of underlined mandatory words there. Or the direction of a stationary or placed mass would initially move.
I must have missed 60 minutes. What are you saying?
Okay, interesting. AQA likes to do things a little differently. I don't disagree with these definitions, but it's different than what I was saying about what field lines actually do. But maybe you go back what is represented by the field lines, and that is true. It's the direction a mass or object would move. Okay, it's the direction of force that acts on a mass in a gravitational field. Okay, like I say, AQA likes to do it a bit differently. Yeah, so the lines are closer together, so the field is stronger. So I guess because they've talked about strength being related to distance between the field lines in part 2, you wouldn't mention it in what's, the purpose of the field line. What's represented is the question. Okay, anyway, it's higher. So all you need to say there is the lines are closer together and it's got a higher, is a higher density than the surrounding material.
Did that go the way you thought it was going to go? Nope.
Okay, I guess I was thinking of a shorter radius, but I guess that little area on the surface, we're not changing the radius. We are just having a denser region. Okay, fine. Force is stronger does not gain the first mark. So for second mark, allow more mass at K. So more mass or more density, not being closer. Very peculiar, AQA.
God, so stupid. What a dumb question.
Okay, and then what would happen? The ball would speed up or accelerate as it moves towards K because the potential is lower at K, or the angled field lines between J and K have component towards. Draw, which I can't do on here. The equipotential line that passes through point N. Do not extend your line beyond the given field lines. Okay, well, you are going to want to draw your line perpendicular to these field lines, and so it's going to kind of be a bit of a parabola. If you follow my cursor here, it'd be a bit parabolic, I would say. Okay, they've drawn a diagram here. Oh, okay, interesting. I'm not as parabolic as I thought. Yeah, I probably would have realized that had I been allowed to draw on the screen. But you can see that in this case, this isn't quite perpendicular. I don't know if I agree with this. This right here is clearly not perpendicular. Neither is this. Okay, line drawn should be approximately cross the field lines at right angles, like we said. A mark is given if the line is symmetrical top to bottom and it bend to the left. So you need something like this. Okay, this is perpendicular. I agree with this second line on the right here, but this here I don't see. I think this should probably go out straight. Take a look on the right if you'd like to see the rest of that. We've got Edexcel Advanced Physics 1, Paper 1 from 2018. Okay, Part B. This graph shows how potential varies with distance from the center of a charged sphere. Air molecules will be ionized if the electric field strength exceeds 3 million volts per meter. Deduce whether air molecules will be ionized at a distance of 30 centimeters from the center of the sphere. Well, electric field strength we've seen is this potential gradient, isn't it? And if you look, we've got potential versus distance. So this would be a potential gradient. So we'll go 0.3. Is this point right here? And we need to draw a gradient to this curve. My gradient here is a potential gradient, so I get 5 times 10 to the 6. So it is going to be, and that's of course volts per meter. So I believe we have a gradient which is higher than this, and so it seems air molecules will be ionized according to my calculations. All right, a magician did a trick which he claimed was the most dangerous ever. He positioned himself midway between two charged spheres, which were separated at a distance of about 2 meters. Each sphere was charged to a potential that would cause ionization at a distance of 1 meter. So he was in between, should be getting ionized. He wore a protective suit of chainmail and a helmet consisting of a metal cage. This is a Faraday cage, isn't it? Protective suit and helmet were earthed to a potential of 0. A scientist said, "There is no danger in this, and I would happily do it tomorrow." Explain whether this statement is justified. So the scientist giving a little dig at this musician, saying it's the most dangerous thing. There is no danger, is there? I think all the current is going to run through the ground. It's been grounded, like I was saying. Okay, and so we've talked about that. I want to bring it to, if we have a hollow sphere and there's charge on it, the charge will be all distributed around the surface of this hollow sphere, but there will be no charge inside. Okay, and what's the potential? What's the electric potential inside of that sphere? The electric potential inside of these spheres is 0. There's no electric potential inside. And if there's a person inside of this cage, then there's no electric field, so there is, right, and of course if electric field strength is our potential gradient, if this is 0, then I would say there's no voltage either. Obviously there's a distance, obviously there's a radius, but there's no potential difference going across. So I would say, he's not going to feel anything. Let's check our marks out here. Right, so what did we calculate? Oh, I got 5.0, they got 5.3, that's fine. So let's see, tangent point correct, 4 marks. Tangent point correct, triangle with a base of at least 0.4. Yeah, I had that. I've got my calculation, and I'm within the range they specify, so that's fine. So would ionize? Yeah, would ionize. So that's what I've done. I've got the 4 marks. An alternative method here, correct value at 0.3. You could have done this. 1.6 times 10 to the 6 volts is the electric potential at this distance here. And you could have said, we also know that electric field strength is this potential gradient. So in other words, it's KQ over R squared. You're just reading those 2 points off the graph. It's 1.6 times 10 to the 6 divided by the 0.3. And if you do that, there's where you get your 5.3 times 10 to the 6. So you don't have to draw a gradient. You could simply just do this point and just divide the value by that value. Okay, what about this magician versus the scientist? There cannot, so can't you have potential difference across the body because he's inside. There's 0 electric field strength inside the cage, inside the hollow sphere. Okay, because there's no potential gradient is what we had said. We also said that current wouldn't go through his body. There'd be no charge to conduct. So that's fine, except reference for Faraday cage for here. Okay, so well done.
Hold these. No. Like this. What are you doing?
Oh, I just want to see if my interocitor can withstand a sudden charge of 60,000 volts.
What?
Yeah. It works.
Okay, and this is a component 2 paper from the WJEC Eduqas, and this is from 2018. Use the principle of conservation of energy to show the critical density of the universe is given by this. Alright, well we can start by saying that the mass of the entire universe, so 4/3 pi r cubed, times rho, which is the density of the universe. And let's put that, that's all the mass within a certain shell, okay? A spherical shell. And what else do we have going on, right? We know that the principle of conservation of energy. So we'll say that all of the kinetic energy is equal to all of the gravitational potential energy. Now, you know, we don't just do an MGH. You know we don't do that. We need to do the mass times the gravitational potential. What's the gravitational potential? It's G big M over R. The little m's are going to cancel whatever was out at that shell at the very edge. Here, I'm gonna just flip a few things over. I'm going to make this a V squared R over 2 over 2G. And I'm going to say this is rho. I'm going to instantly flip the 4/3 and make this 3 over 4 pi. Okay? And that'll be over R cubed, won't it? Okay? So that's what rho is. I'm going to continue on. Rho now. So you can see here, it's starting to shape up nicely. I've got 3 over 8 pi. That's nice. And then, what's going on? Where's this h naught come from? Well, of course, we know our velocity, this is going to come from the Hubble equation there. Okay, we know that this distance is the furthest extent of the universe there. We can make that an r if we like. That's fine, can't we? Okay, now if we square this, you'll see that when we plug this in, that's where we get our h naught squared. And then would you looky at this? R squared times r is going to cancel with the r cubed on the bottom. And the g is left. And by Jove, I think we've done it. Use the above equation to show that the critical density of the universe corresponds to approximately 5 atoms of hydrogen per meter. If we plug in our Hubble constant and universal gravitational constant, we get a critical density of 8.7 times 10 to the negative 27 kilograms per cubic meter. Okay, what's the mass of a hydrogen? I'm going to divide by the mass of a proton, because that's what hydrogen is. 1.66 times 10 to the negative 27. Hold on a minute. They're both to the power of negative 27. That's interesting. But this is just kilograms. So it's really, really, really tiny, infinitesimal fraction of a kilogram. Okay? Whereas this is how many kilograms per cubic meter. Now when we divide these, 8.7 divided by 1.6. I get approximately 5.2. I get 5.24, and that's now kilogram. Oh, that's not kilograms. What is that now? That's just protons. Protons per, or hydrogen atoms per meter cubed. Because technically, I've done this as kilograms per atom, isn't it? We'll just quickly look at the mark scheme. So we've done the equation. We've done what we needed to do. I think we got 4 marks for the first one. We did the same thing here. We've calculated what the critical density was. We've divided, and we got that many atoms of hydrogen per cubic meter. You could have done it a couple other ways. You could have done it using molar mass. You could have done Avogadro's number. You could have done a bunch of things. You could have figured out the density of 5 atoms. You could have, but do it the way you like and the way you're going to be quick and mistake-free. Okay? On the same paper, we've got a number 5. Diagram shows key features of the rotation curves for distant spiral galaxy. They explain how these features relate to the structure and motion of the galaxy. A lovely little QER. if you're studying the WJEC or Eduqas curriculum, you will have seen this, you will have talked about this. This kind of, I remember doing this with my class a few years back, and we've got is this dotted line is the expected curve of what we should see. We should see, as we move further away, the rotational velocity kind of drops with that. But what we actually observe is it actually is quite constant. And so this gives the discussion of dark matter and that sort of thing. In the interest of time, I'm going to jump right to the mark scheme and see the things that we could be talking about in here, the indicative content. Okay, so you can reference the, the centripetal force being equal to the gravitational force, okay? Or something along those lines. You could say, hey, your velocity, if you rearrange, you can say your velocity is going to be equal to gm over r square rooted. You can talk about how for small r, the theory seems to agree. We see that on observation that the v squared is proportional to the observed mass. Observations show a concentration of mass in the center leading to, and then a continued point. For large r, the theory predicts that it's proportional to the reciprocal root of r. All right, it's inversely proportional to the root of r. As you see here from the dotted. Observed line shows that v is constant, okay, or it's much greater, as we said. I mean, really here, explain how these features relate to the structure and motion of the galaxy. I've talked about some of the features. I've said, hey, we expect this, but it's actually this, blah, blah, blah. But now we can get into the explaining a bit more, yeah? You can say that this indicates that the mass is proportional to the radius, or the mass is greater than expected, is what we saw. Mass is not observed, however. We don't see that mass. And this is what the dark matter, there's a possible link to Higgs boson. I don't know if you've done the particle, what you might, in WJEC you don't talk about that too much. All stars orbit the center of the galaxy. The curves extend beyond the visible disk. You see this curve, they extend beyond the visible disk. So anything kind of out near the galaxy, you would expect to kind of feel something, is that what they're saying? Orbital speeds are measured using the Doppler effect. These are the types of things they want you to talk about. So you're not being asked to explain, it's just how they relate to the structure and motion. All right, this is something you're going to want to practice if you're in the Eduqas realm.
Okay, and this is a Cambridge Pre-U Paper 3 from 2018. State Kepler's 3 laws of planetary motion. Right, so we know that the first law of planetary motion is that orbits are ellipses, and the sun or the star or the planet, whatever the larger mass body will be, is at one of the foci. All right? So write that out as you will. We know that the second law is that if you draw a line from that planet to the satellite, or from the sun to that planet, if you take equal intervals of time, they will sweep out equal areas. Okay, that's because even though the radius is shorter, when you are closer to the sun or the planet, then you are traveling faster, and so you'll cover a larger distance even with a shorter radius, and vice versa on the opposite side. But the areas are equal. And then the last bit is that the square of the period is proportional to the radius cubed. Now the radius can be the, if it's close to being a circle, we can talk about its average distance, its average radius, or we talk about the semi-major axis usually, okay, when it's an ellipse. And part B here, they basically want you to derive what that law is using Newton's law of gravity for a circular orbit of a satellite around the Earth. We did that in question 1. I'm not going to repeat it. We'll move on. Calculate the gravitational potential energy of the person. So this is an 80 kilogram person on the surface of the Earth. So because we are taking the radius of the Earth into account, we know it will not be mgh. It's going to be m times gm over r. Okay, you plug it all in and you get your answer. We are at basically negative 5 billion joules. That's the amount of energy you would need to overcome to free yourself of Earth's gravitational pull and be an infinite distance away. Explain why there's a minus sign. Well, that's kind of what we're just talking about. We are in an energy well, and I've said it before a few other times, but we defined being infinitely far away as being our potential of 0, and therefore if you go back towards that more massive object, you are in an energy well. Something to that effect. Calculate the minimum initial speed a projectile leaving the surface of the Earth must have to escape. Okay, so we saw this before. We've basically established that we know it needs to be the root of 2gm over r, and if we do this, we will get our escape velocity. So if I go and plug in all the numbers there, square root of 2 times 6.26 times 10 to the 7. So we get, yeah, this is what we usually get. We usually get around 11,000. Or 11, they say sometimes 11 kilometers per second, 12 kilometers a second. Looks to me like maybe 11.2 is all you're going to get. So there we go. That's escape velocity for Earth. And we check our answers. Yes, so they've rounded it up to 3 significant figures, as they usually do for the pre-U. And let's go back up to the top. So planets move in elliptical orbits with the sun at one focus. Okay, so that's underlined. You need that. Sun-planet line, that's a nice way of putting it, sweeps out equal areas in equal times. There's another question, I think, in part 2 where it's a 2-marker or 3-marker, and you really got to be careful about that sun-planet line, so make sure you mention this, okay? And the orbital period squared of the planet is proportional to the mean distance of the sun cubed. That's what we had said, okay? And we derived that. There's other ways we've done this. We've done that on the first question. You can go back and have a look. We have already looked at that answer. That's fine. We've got that number. Okay, substituted in, and we got the correct sign. It's negative. And why is there a minus sign? Okay, so it's because 0 gravitational potential energy has been defined at being infinitely far away. It's defined at infinity, so work needs to be done to reach 0 gravitational potential energy to move away. Or you can say it's because we've defined that way, and so since that's infinity, as you go in, gravity is attractive. You are doing work. You are doing not work against gravity, but with gravity, and so you would have a lower amount of energy, which would make it negative.
This is an A2 Unit 4 paper from WJEC 2017. We've got a planet, Kepler 186f, and it orbits the star Kepler 186. I love these names. Show the radius of the orbit of the star around the center of mass of the system, okay? So this is a much heavier star. The center of mass won't be down the middle. The center of mass might be kind of out here somewhere, kind of close, who knows? And perhaps you remember this formula where you've got x here is the distance from the star to the barycenter, the center of mass, and this is the equation that you've used in WJEC. You plug in the numbers provided and you get your answer. I think we'll move on. The period of orbit is 130 days. Calculate the orbital velocity of the star. So here's the formula that you're going to use. You need the orbital velocity. You need to change your days into seconds, and then you can get the orbital velocity. Let's take a look at the answers. So for the first question here, you plug in all the bits, you plug in the masses, you plug in that distance they give you between them, and they say here that plus 0.92 can be omitted from the above equation. What they're saying is that this mass is so small it won't really matter. This is 10 to the 29, this is 10 to the 24. They're saying it won't matter, at least in the bottom bit. But it's 513,263, okay? And your velocity here ends up being 0.287 meters per second. Calculate the potential energy of the star-planet system. Yeah, potential is Gm over R, okay? And the potential energy, the gravitational potential energy, is Gm little m over R. Yeah, you could also say, if you take a look at what this really is, it's the universal gravitational force times another radius, isn't it? Okay, because Fg is Gmm over R squared times the R. There you go. All right. The other way to look at this is if you're used to just down to the closest surface of the Earth, you've got mg is mgh. Yeah, mg is the weight. It's the gravitational force times that height. Okay, so there's your dimension of a meter of length there. Okay, that's your formula. Plug it in, and again, you'll get your answer. In fact, the planet has a slightly elliptical orbit. Explain how conservation of energy applies to this elliptical orbit. we know that when this planet is at its aphelion, that is furthest away from the sun, it will have, a slower speed. It'll have a lower kinetic energy but higher potential energy, because remember that going out to infinity gives us a potential of 0. So the further we are away, the less negative we are. It will have a greater potential. But as it moves to perihelion, closest approach, it will have a faster speed, it will have a greater kinetic energy, but it will have a lower, and I mean more negative, it'll have a lower potential energy. I'd say something along those lines. So there's your numbers, you plug in, you get your answer. Realizing kinetic energy is involved, correct variation of with distance for kinetic energy, as I said, or velocity, or as PE increases, KE decreases. So something along those lines, which I had said. You're really going to want to practice. I find these WJEC mark schemes, they're just telling you what to give the marks for. It's really up to you to put your solution together and craft a well-written answer. And that's why we practice.
Okay, and that's all we've got time for. We'll continue more questions of the same type and maybe some new ones in the second video.